So first, thank you that you came here for this very late session. I hope that it will be interesting for you. So it will be quite technical session. I promise there will be no marketing bullshit here. So and hope that you'll learn something new and interesting, and would like to have questions on this topic. So the presentation today is mainly about QEMU and how QEMU works, how QEMU can be optimized for I/O, despite QEMU does not present in the title of the session. So we'll see first how QEMU works, what is the QEMU execution model. This will help us understand why there are different I/O modes in QEMU, and that will lead us to the important question of what is actually iothread. Then we'll see why we need to use iothread, what is the performance impact, what are the issues with and without it, and then we'll see how we can use iothread in QEMU and libvirt, and we'll see the current status of CloudStack, how CloudStack can support or cannot support this. So let's start with how QEMU works, what are the execution threads of QEMU, and one important note here, when in this session, when I say QEMU, we shall all assume that we're talking about QEMU KVM. So QEMU have many different modes of operation, user space, different emulation modes, but we'll consider here only QEMU KVM. With KVM virtualization, because this is the area where we are interested in clouds and virtual machines. So QEMU implements a hybrid model of processing asynchronous events. So there is one main thread that runs event loop that processes all the I/O events in sequence, and because of this, that it is a single thread that processes all these events, it requires that all the event processing should be asynchronous and non-blocking. For tasks that require longer time or more heavy workload, there are dedicated worker threads created. Some of the threads are permanent, some of the threads in QEMU are created on demand. And the third one of threads that are created that exist in QEMU are per vCPU threads. These are the threads that actually runs the guest code, the instructions of the guest code. So in the typical process, QEMU KVM process, you can see we'll have these threads. So the first one is the main thread with the same name. There is a worker thread that does some different stuff, I'm not sure exactly what. Then actually we have several different worker threads. This thread, iothread, has nothing to do with iothread. It's a complete nightmare with a naming in QEMU. So iothread is used for three completely different stuff, not related. Then we have for every virtual CPU separate threads and some other worker threads. For example, VNC thread that is responsible for encoding the video information because it requires some CPU and it shall not affect the execution of the virtual machine. So now let's go to the topic, what is iothreads, but before we can answer this, we need to understand what are the different modes of asynchronous I/O in QEMU. So at the moment, QEMU supports three different interfaces and three modes for executing asynchronous I/O operations. As we saw in the previous slide, the main event loop needs to execute non-blocking tasks for all different stuff, including the I/O operations. And there are three different ways that I/O can be executed non-blocking, so it will not block the main event loop. The default one in most builds of QEMU is the so-called threads asynchronous I/O. In this mode, all I/O requests are routed to separate worker threads where they are executing, and they are using blocking syscalls. Because they are using blocking syscalls to prevent blocking of the main event loop, they are executed in a separate worker thread. This is the default one. It is the safest way QEMU can work. It works in, I think, in any environment with block devices, with a file system. But it has some disadvantages we will see later. It has the worst performance of all the three modes. The next one is it's so-called native. Again, very bad naming. It comes because it uses native Linux asynchronous I/O syscalls. So all the I/O requests are executed from the main event loop, but they're using asynchronous Linux syscalls that should, in theory, always return immediately without blocking the process. So this mode has a much better performance because it doesn't require inter-thread communication and synchronization. It doesn't require any locking to execute this. And native Linux I/O should be faster compared to blocking syscalls. The third mode is io-uring. It's a very recent development. It was introduced maybe 2 years ago in the Linux kernel and provides an asynchronous interface using request and completion rings that can be accessed directly from the user space. So there is a separate io-uring API, and it is included in the recent version of QEMU. It is promised that this is the best performing mode of I/O, but we'll see later that there are some issues with it. So today we'll focus on the native Linux I/O mode of operations. It can be easily identified if you have in the QEMU. So let me see here. Do I have? Okay. So if we have this option in the device drive parameter, AIO native, or in libvirt, it is defined in the driver element with this optional attribute ionative. So this enables native AIO. So let's see what's the difference in practice when we have these two different modes of operations. So this is the threads of the QEMU process when the virtual machine generates a lot of I/O traffic. So you can see here that QEMU has created a lot of worker threads that handles I/O requests. So I forgot to mention that here is the list of the threads, and this is the number of bytes that each thread has read. So you can see that all the read operations are executed by separate worker threads. In practice, there are about 64 worker threads spawned during heavy I/O operations, and after a few seconds of idle time, they are destroyed. So this is the default mode if you do not specify anything. So if you specify I/O native, then you can see that all I/O operations are executed from the main event loop, and there are no additional worker threads spawned. So in most cases, this works well, and this is the preferred configuration, although this is not the default one. So having asynchronous IO running from the main thread can create some problems, and that's why in the last maybe since 2014, QEMU has implemented a mode where you can have a dedicated thread for running Linux native asynchronous I/O. So it can be enabled in libvirt definition with this element, iothreads, and the number of iothreads. You may have more than one. And then on the device, you can specify which iothread will serve requests from this device. With this configuration, there is a dedicated IO thread that is a persistent IO thread. It's always there, and all the IO requests are served from this thread instead of the main loop. So, what are the and actually, this is the main topic of this talk, this mode of operation where we have a native I/O, but they are executed from a dedicated thread, I/O thread, instead of the main event loop. So let's see what are the performance benefits of using I/O thread. So this is a test made from a virtual machine that has a virtual disk backed by a local NVMe device on the host. In the virtual machine, we have run a FIO random write with 4K block size, Q depth of 1, to measure what is the latency of the write operations. And these operations are executed by the NVMe row device, so the virtual disk is mapped to a row block device on the host that is NVMe device. We try to eliminate as much as possible of the actual device, storage device latency and impact. So the default mode, that is, we call it iothreads. So it has about how much 60 microseconds to complete the write operation. With Ionative, the latency is about 40 microseconds. That is significant improvement. And if we have a dedicated IO thread, so if we have Ionative and iothread enabled, then we can get almost down to 20 microseconds. So it's almost 3 times less latency for processing the IO operations. With slow storage devices, this 40 microseconds doesn't make a big difference, but if you have fast storage like local NVMe, it may make a huge difference, especially for workloads that are sensitive to the latency, like transactional databases that does not have a huge IO queue, but need a fast response time. So you can get several times better performance. So it is important also to know that this is only one test. In different environment, you can see different results. Maybe this is one of the extreme cases. In many other cases, you may have a much less difference between the 3 modes. In some cases, for example, when you're using not a block device, but QCal image on top of file system, you may even worse performance using Ionative compared to iothreads. So when you decide what mode and what configuration you need to operate, we strongly encourage you to always make tests that are as much as possible close to your production environment and production mode. So why don't we talk here about IOUring, and we're talking about Ionative with iothread. So the main reason is that Linux native asynchronous I/O is universally available. This interface is more than 10 years old in the kernel. It's available in QEMU for almost 10 years. it is everywhere. On the other hand, ioURINC is very recent, and there are a lot of dependencies that are required, that has to be satisfied in order to use ioURINC. So in many cases it will work, but in many cases it will just not be possible to use ioURINC. It's still not very popular because of this. So the requirements to run ioURINC is to have this is the host kernel. Host kernel should be 5.1 or later, so this is the easy part. QEMU should be version 5.0. It's an important asterisk here. And you need libvirt version 6.3. In CloudStack, there is a support for ioURINC that is introduced in 4.16.2, I believe, but there was a issue with it that was fixed in 4.17. So the first version that actually works well with ioURINC is 4.17. So what this asterisk next to QEMU means, so even if you have QEMU with a recent version, in many cases ioURINC supports it's not built, it's not compiled in the QEMU. So the QEMU that comes with all Red Hat 8 and its derivatives like Alma 8, Rocky Linux, they come with QEMU that is the correct version, but it doesn't have a ioURINC compiled in. So if you try to use this binary, then you end up with such an error. And in general, it is not guaranteed that you have this available in your configuration yet. So probably in a year or two, it will be much better, but today it's still difficult to rely on this feature. Also, there are some reports says that ioURINC has a great performance improvement over Ionative, but our test shows that this is true only for some specific workloads and specific use cases. In general, you might not be able to see such significant performance improvement. We have seen cases without any performance improvement compared to native I/O, but again, this depends on the environment and on the workload. So for you, it might work very well. Yeah, this is a link to one of the posts in the for the very first version of QEMU where it was introduced, ioURINC, and it shows a really great performance benefit, but this is not always the case. So Linux native I/O is in many cases much better than the default thread mode. However, it comes with some issues. So if you try to Google with a QEMU and this error, you'll find hundreds of results. So, some of them are back from 2012 when the Ionative was introduced, and there are very recent issues still with this mode. So the reason for this are very different, but all they have, I believe, the same source, and it is that with Ionative, IO requests are executed in the main loop, and not always these asynchronous events are true asynchronous, and sometimes they might block that will cause the main event loop to blocks. So one of the main contributor of QEMU, so Stefan Hajnutzi, I hope I pronounce his name correctly, says that the main problem is this from his blog. The main problem is that this asynchronous syscall is just not asynchronous in some cases. It can block. And he listed some use cases where this is on when the requests are for file access, and the file system might block the operation. But we have seen this problem not only for file I/O operation, but also for I/O operation on the roadblock devices. So, for example, we have this configuration where we have a virtual disk that is using raw image directly on the block device. In this case, it just happens to be a StorPool, but on any block device. If there is a heavy I/O, it can cause this problem. So here's one example. When I prepared this presentation, I easily reproduce this in our lab. So we have a virtual machine, again with a virtual disk mapped to a block device, raw block device. And in the guest, in the virtual machine, we run some heavy I/O requests. In this case, sequential reads with block size of 128, I/O depth of 128, and we executed them directly on the virtual disk, and left to run this test for a few minutes. So at the same time, on a router, we start pinging the virtual machine, the interface on the virtual machine. And after a few minutes, we can see that the virtual machine just stopped responding. It doesn't respond on the console, on the network interface, so it's completely dead. So in this case, we see it's about 15 seconds. It's stopped responding for 50 seconds. So even if you assume that the block device, blocks operation and stops, there is no excuse to have a condition when the virtual machine is unresponsive on the network interface. And as a result, we can see in the guest, the kernel has exactly the same report that CPU has stuck for, one of the CPU has stuck for 23 seconds with a stack dump, and later on we have for something like several minutes until the virtual machine completely died. So this is caused again because of this asynchronous I/O calls, kernel calls in the host actually block, and the QEMU emulator does not accept this, and it cannot handle well this situation. It expects that all asynchronous calls are really asynchronous. So what is the solution? Oh, before this. So how this looks like from the hypervisor. So from the hypervisor, it looks like this. The guest kernel submits a lot of I/O to the virtual disk. The QEMU process handles this and submits the I/O operations to the host kernel and to the host block device via Linux native I/O. And it is the main thread that also processes all the hardware emulation, interrupts, timers, and so on. So the host kernel, at some point, host kernel decides that this thread generates a lot of traffic, and it blocks it by blocking the I/O requests. As a result, the main thread just stops at that point and cannot serve its main task to emulate hardware and serve other tasks in the virtual machine. So the solution is to configure a dedicated thread for the I/O operation. So we just enable iothread and define here that our virtual disk uses this iothread for I/O operations. We can see here is the iothread with all I/O operations. And if the kernel decides to block I/O operations, it will block only this I/O thread, this one, not affecting the main event loop. So as a result, the I/O operations in the virtual machine will block. That is completely okay, but the rest of the virtual machine will continue to work as expected. So the virtual machine will continue the virtual CPU will continue to operate and to run instructions. Hardware will be emulated. Virtual network will be running. So everything is okay. So exactly the same test with iothread enabled. We run the same load in the virtual machine, and we can see here there is no any stalls in the network traffic. We can see it's 0.3 millisecond is the maximum delay of the network. So there is no any impact on the network traffic. At the same time, we can see this is the report of the FIO test in the guest. We can see that we had a maximum delay of about 2 seconds. So the block device, the virtual block device, has blocked for 2 seconds. That's completely more than expected, but this doesn't affect the rest of the virtual machine. So I would say there are 2 main reasons to use iothread. First is this is the first one to prevent this unexpected behavior and blocking of the virtual machine. And the second one is better performance that you can get with this. So even if the performance in your use case is not better compared to using the native mode or without iothreads, we still recommend using iothread because of this problem. So how we use iothread, I've already showed this in examples. Let's see. Okay. So first since we are always using libvirt to define virtual machines, I'll show here only the libvirt interface. So first we need to enable iothreads, and here we can specify the number of threads, iothreads, and then we need for every block device to specify whether it will use iothread and which iothread it will use. So unfortunately, there are 2 different ways to define this depending on the type of virtual block device. So if the block device is virtual block, then you can specify directly on the device element, in the driver element, you can specify iothread. And if you are using virtio SCSI drive, then you have to specify this not on the drive, on the disk element, but on the controller, the corresponding SCSI controller. So this is the only specifics. Everything is the same. So it's pretty simple. It's straightforward, and it just works. One question: how many iothreads do we need? So I don't think there is a definitive answer to this, but our experience is that 1 iothread is much better compared to no iothreads at all. And in 99% of the cases, you don't have any performance improvement if you have more than 1 thread. So 1 thread is probably capable of serve maybe about 100,000 IOPS. Unless you have a very big virtual machine with a lot of virtual CPUs and hundreds of thousands of IOPS, then maybe multiple threads will help. But this is very unusual and very specific use case. So what's the iothread support in CloudStack? Unfortunately, the good news was up to here. There is no, at the moment, reasonable support in CloudStack. So CloudStack does not, at the moment, is not capable to specify the IO mode and is not capable to enable iothreads. So when CloudStack creates a virtual machine domain definition, it just left IO mode empty without any specification, and it doesn't create the required elements for iothreads. This means that with most QEMU binaries that have iothreads as default, you use this mode. Well, it's not so bad because this is the safest mode, although not the best performing one. But as we all know, it just works. So no one, or maybe very few, have issues with this. So what are the other cloud management platforms? So in OpenStack, there is an option to define and to enable native IO mode since 2016, and it can be defined per virtual disk or per volume. And iothread is still not in the main tree, but there is a code that is to be submitted there, so we can expect that very soon you have an option to enable iothread per virtual machine in OpenStack. OpenNebula have a native IO since 2014. And again, it can be controlled per virtual disk. And iothread is included in the main tree since version 6.0, that is from April last year. So again, you can define this per virtual machine, actually per template. Before that, there was other option. Before 2012, we have used it with in many configuration with a special add-on that is easy to modify domain definition in OpenNebula without need to patch the main code of the OpenNebula system platform. So I'm not sure what are the other systems like Overt or for example Proxmox, but since these are the most popular in our community, this is where, and definitely CloudStack is behind the other one. So we have some plan to propose a code that will solve this. We will enable this. Unfortunately, we didn't keep to our internal promise to have it available before this conference. We hope we'll have it in the next couple of months. We'll propose it as a feature in some of the next releases. But if someone decide to help with this or to implement it, we'll be really happy to see this. Yeah. So I think we have about 10 minutes.
I have a question here.
We ran into this issue a while ago, so I think I would like to offer our help in fixing
this one.
Yeah,
yeah,
for sure. Yeah, I think we can just have a talk later and help each other. So very. I would like to thank you for your presentation. It was nice and welcoming, and yeah, I'm really looking forward in getting this along. So if we can help each other, we should.
Thanks. One note again. It's not necessary that it is caused by this issue is caused by I/O operation and blocking I/O, because it may be caused by different blocking events in the event loop, not only disk I/O, but yeah.
Another
Please.
question?
Well, slight remark. I partially implemented this already in the Java code. It's there in for like 50%, but it was never finished. So, we have the root disk controller setting, which we can set per VM. So we can probably also add an additional setting there, what kind of IO threads we want to use. But in the meantime, I also think you can use the libvirt hooks. So whenever you spawn the VM, you can modify the XML while the VM is being spawned outside the control of CloudStack. So with a bit of Python code, you can probably already inject this right now. Yeah, so we were thinking about this, but it is a good workaround until we have this in CloudStack. Honestly, I guess this is 2-3 hours of work. And then so we have exactly this for OpenNebula, but with OpenNebula we have a plugin that is between the OpenNebula and libvirt, and not using libvirt hooks. I'm not sure if you can have in libvirt you can have a hook on create domain.
Just not sure. I know that you can have it, for example, during live migration, but not sure if you can do this like create domain, and also you need to handle live attach and detach of the drives. Yeah, thanks, Guido.
More questions?
So I have a few questions. First, do you have any plan on testing the iothread on other operating system, for example, Ubuntu 20.04?
So we've made some tests. Unfortunately, I don't have here the results that didn't with a rollblock device, because this is the environment where we work, where the virtual disk is mapped to a rollblock device. Didn't show significant improvement. I know that Guido last year has a good presentation on this topic, and he had a very impressive results with iothread. But in our environment, it didn't show significant improvement. So definitely we will continue on this. At the moment, we don't have any. We cannot share any specific tests.
Okay, so do you mean the improvement compare with the
Native IO
native
plus
IO.
iothread.
Okay, I see. Thank you. So
Because this is the fastest mode that we know works at the moment.
okay, thank you. So next question. So what disk types and image format support the native IO and iothread? So I mean, you think here the disk type is block. So what about other disk types? For example, files or self, I don't know, RBD. Yeah.
So we haven't tested it with other backends, but there. So in 2000. So I saw some reports from 2012, 2014 that native IO has issues with QCOW images on X4 file system, especially with QCOW and also with non-tick provisioned images with sparse provisioning. It doesn't behave well. I'm not sure whether, and when I'm saying not behaves well, I mean data corruption. And I don't know whether this is solved or not. So you have to make your research by your own whether you will use native IO on a file system.
Okay, thank you. For this issue, I'm glad to see that you have a solution. So have you tested with different operating system and different Linux kernel version in the VM or on the host?
Yeah, I think this was tested on, let me see, I think this was tested on Ubuntu 20. But the same problem, not sure if we have seen the same problem is, no, actually, this was tested on Alma 8, and we first saw this on Ubuntu 20.
Okay, thank you.
Anyone else? Then I think we need to heartily thank Venko for his wonderful presentation.
Thank you.
Thank you.